This is the second part of the video containing solutions to end semester examination. The subject is analysis and design of algorithm. Let's begin. Fifth, derive the time complexity of iterative and recursive versions of Fibonacci. The Fibonacci sequence is a series of numbers in which each number is in the sum of two preceding ones, starting from 0 and 1. The first few numbers in the sequence are 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, etc. The iterative version of the algorithm uses a loop to calculate each number in the sequence. The time complexity of iterative algorithm is big O of n, where n is the position of desired number in the subsequence. This is because the algorithm needs to calculate each number in the sequence once, and each calculation takes place in constant time. Here is the pseudocode for the iterative version of Fibonacci algorithm. Here is the code. Now the recursive version of Fibonacci algorithm uses a recursive function to calculate each number in the sequence. The time complexity of recursive algorithm is order of 2 to the power n, where n is the position of the desired number in the sequence. This is because each call to the recursive function generates 2 more calls until the base case is reached. Therefore, the number of function calls grows exponentially with n. Here is the pseudocode for recursive version of algorithm. In general, the iterative version of Fibonacci algorithm is faster than the recursive version for large values of n. However, the recursive version can be useful for smaller values of n or for determining the concept of recursion in programming. Sixth question. Explain chain matrix multiplication with suitable example and discuss its practical applications. Chained matrix multiplication is the problem of finding most efficient way to multiply a chain of matrices together. This problem arises frequently in many areas of computer science and engineering, such as in computer graphics, machine learning, signal processing, and optimization. In the chain matrix multiplication problem, we are given a sequence of matrices A1, A2, A3 up to An, and we want to find the product A1, A2 up to An. There are many ways to parenthesize this chain of matrices, and each parenthesization has a different cost, which is the number of scalar multiplications required to compute the product. The goal is to find the parenthesizations that minimizes the total cost. For example, suppose we have 3 matrices A, B and C with dimensions 10 into 20, 20 cross 30 and 30 cross 40 respectively. The most naive way to calculate the product ABC is to first compute AB, which requires 10 cross 20 cross 30, that is 6000 scalar multiplications, and then multiply the result by C, which requires another 10 cross 30 cross 40, that is 12,000 scalar multiplication. Therefore, the total cost of parenthesization is 18,000 scalar multiplications. However, there are other ways to parenthesize the chain of matrices that can be more efficient. For example, we can first multiply BC, which requires 20 cross 30 cross 40, that is 24,000 scalar multiplications, and then multiply the result by A, which requires 10 cross 20 cross 40, that is 8,000 scalar multiplication. Therefore, the total cost of this parenthesization is 32,000 scalar multiplication, which is higher than the naive approach. The optimal parenthesization for this example is to first multiply AB, which requires 10 cross 20 cross 30, that is 6,000 scalar multiplications, and then multiply the result by C, which requires 10 cross 30 cross 40, that is 12,000 scalar multiplications. Therefore, the total cost of parenthesization is 18,000 scalar multiplication, which is the same as the naive approach but requires fewer scalar multiplication. Chained matrix multiplications has practical applications in many fields, such as in machine learning, where it is used for computing the dot product of two high dimensional value vectors. It is also used in signal processing for computing the convolution of two signals and in optimization for solving linear programming problems. Additionally, efficient algorithms for chain matrix multiplications are important for improving the performance of scientific simulations and large-scale data analysis. Seventh question is, use a critical lens to describe traveling salesman problem TSP using dynamic programming and discuss its potential benefits and limitations in solving the optimization problem. The traveling salesman problem is a well-known optimization problem that involves finding the shortest possible route that a salesman can take to visit a set of cities exactly once and return to the starting city. This problem is known to be NP-hard, meaning that it is computationally expensive to solve for large numbers of cities using exact methods. Dynamic programming is a powerful technique that can be used to solve the TSP problem by breaking it down into smaller subproblems and then using the solution to those subproblems to solve the larger problem. In context of the TSP problem, dynamic programming involves solving the solutions to subproblems in a table and then using those solutions to compute the optimal solution to the entire problem. One potential benefit of using dynamic programming to solve the TSP problem is that it can lead to a significant reduction in computational complexity compared to brute force methods. Brute force methods involve trying every possible route through the cities, which becomes impractical for a large number of cities. Dynamic programming, on the other hand, can reduce the number of possible routes to consider by breaking the problem down into smaller subproblems. However, there are also limitations to using the dynamic programming for the TSP problem. One limitation is that it requires a significant amount of memory to store the solutions in subproblems in a table. As the number of cities increases, the size of the table grows exponentially, which can become prohibitive. Another limitation is that dynamic programming requires solving all possible subproblems, which can also become impractical for large number of cities. Furthermore, dynamic programming does not always lead to optimal solution for the TSP problem. This is because the problem is NP-hard, meaning that there is no efficient algorithm that can always find the optimal solution for large number of cities. In practice, dynamic programming is often used in conjunction with heuristics or other approximation algorithms to find good solutions to the TSP problem with a reasonable amount of time. In conclusion, dynamic programming is a powerful technique for solving the TSP problem and can lead to significant reduction in computational complexity compared to brute force method. However, it also has limitations in terms of memory usage and scalability, and may not always lead to optimal solution for large number of cities. Nonetheless, dynamic programming remains an important tool in optimization toolkit and has been used to solve a large variety of real-world optimization problems in the field such as logistics, transportation, and manufacturing. Question 8. Write a non-deterministic search and sort algorithm. Non-deterministic algorithms for searching and sorting. The design of non-deterministic algorithm is based on three major functions: select, success, and failure. To declare the success or failure, verification process should be designed. The verification process is given below. This one is for the searching algorithm and this one is for sorting. Question 9. Analyze and compare the class P, NP, NP-hard and NP-complete and provide examples of each. P, NP, NP-hard and NP-complete are classes of decision problems that are used in computational complexity theory to classify problems based on their computational complexity. First is P, polynomial time problems. These are decision problems that can be solved by an algorithm in polynomial time, meaning that the running time of the algorithm grows no faster than a polynomial function of the size of the input. Examples of P problems include sorting, searching, and matrix multiplication. NP, non-deterministic polynomial time problems. These are decision problems that can be solved by non-deterministic Turing machine in polynomial time. A non-deterministic Turing machine is a theoretical model of computation that can try multiple possibilities in parallel. However, no known algorithm can solve an NP problem in polynomial time on a deterministic Turing machine. Examples of NP problems include the traveling salesman problem, knapsack problem, and Boolean satisfiably problem SAT. Next is NP hard. NP hard problems are decision problems that are at least as hard as the hardest problem in NP. In other words, any problem is NP can be reduced to NP hard problem in polynomial time. Therefore, solving an NP hard problem in polynomial time would imply that all NP problems can be solved in polynomial time. Examples of NP hard problems include the Boolean satisfiability problem, the Hamiltonian second problem, and the vertex cover problem. NP complete. NP complete problems are decision problems that are both NP and NP hard. They are the most difficult problems in NP and are considered to be the hardest problem in computational complexity theory. Examples of NP complete problems include the traveling salesman problem, knapsack problem, and Boolean satisfiably problem. In summary, P problems can be solved efficiently by algorithms in polynomial time, while NP problems require non-deterministic algorithms or exponential time algorithm. NP hard problems are at least as hard as the hardest problem in NP, while NP complete are most difficult problems in NP and are both NP as well as NP hard.